So today we're going to take a look at some of the newer AI-powered tools in GlobalMapper. I know not all of you may be familiar with GlobalMapper, so we'll introduce the app a little bit as well, assuming my slide moves forward for me here. So I'll talk very briefly about what GlobalMapper is, just so we have some context for the rest of the talk. And then we'll talk a little bit about AI. You know, we see it everywhere these days as a buzzword, how it fits into GlobalMapper, what we're trying to accomplish for our users. And then time permitting, we'll take a quick look in the application itself and we'll run some, or at least look at some models live. I don't know if we'll fully run some, but at least take a look at some as we're going along. So GlobalMapper and GlobalMapper Pro are an all-in-one desktop GIS. The main differentiator between the standard and the Pro version of the app, the Pro version of the app is where you see more advanced LiDAR, photogrammetry, deep learning powered tools, and things of that nature. But in general, you can think of GlobalMapper competes directly with any of the other major desktop GIS softwares. The app supports over 300 file formats. So whether we're talking raster, vector, point cloud, meshes, models, 3D terrain, etc., GlobalMapper supports a huge variety of them. Any of your basic raster and vector processing and analysis can be done in GlobalMapper, whether we're talking about searching, spatial analytical queries, raster analysis and calculation. The app handles all of that. The app started actually as a USGS tool, so its foundation in terrain-based analysis is really one of the cornerstones of the application. Everything from visualization and manipulation of terrain data all the way through profiling, advanced volume calculation, change detection, you name it. Hand in hand with that, 3D analysis, right? So not only is terrain data three-dimensional, but we start looking at meshes and models and photogrammetry and LiDAR and all those things that the app handles. And we have a really powerful set of 3D visualization and analysis tools. Photogrammetry, as I mentioned, a little bit beyond the scope of that talk. But if you're someone who is, collecting imagery with drones, flying UAVs, we have tools for that full photogrammetric process, building your meshes, your models, your point clouds from your drone images, and a lot of the much more that we're going to talk a little bit about today. But so hopefully that gives you just a little bit of a feel for what GlobalMapper is and all that it can accomplish if you're newer to the application. Let's switch gears and talk a little bit about AI, right? What is it? We hear this term often. Many businesses and creators are taking advantage of it in a variety of ways, whether we're talking, chatbots or recommendations on Netflix, right? Technically, AI is a computer science discipline. It focuses on trying to accomplish tasks that traditionally require human-like intelligence. That might be pattern recognition, learning from data, problem solving, and now these days, even content generation, like the graphic on my slide here, right? Literally just a ChatGPT generated image. And I'm sure we're seeing it in our everyday lives. I know even outside of work, I can't get away from it, right? I get X-ray back when I had pneumonia a couple of weeks ago, and they give you the initial, automated AI analysis. Maybe you're someone who does a lot of training and running like I am, and you have a automated coach that optimizes workouts and analyzes your metrics in that regard. So there's a whole bunch of ways we're seeing these AI tools applied throughout our lives. Two key differences that are good for us to understand when we mention AI are the ideas of machine learning and deep learning. And although the difference might seem subtle, it's important because it drives a lot of development and thought around how we're going to use our tools. So something like machine learning, generally speaking, works on smaller structured data sets. It's these days less computationally intensive and requires a bit more user input before some type of processing. So for those of us who have been around a bit and maybe, back in the day you would manually, I'm thinking back to the days of when I was working in the very early versions of Envy and making training data for basic land cover classification. And we'll talk a little bit about modern approaches to that today. The deep learning side of things is really considered a subset of machine learning. And this is where we start to see the leverage of incredibly large amounts or substantial amounts of data. Deep learning generally has much higher computational needs and requirements. These days, all the talk is about graphics cards and GPUs. Users benefit from deep learning methods because it's very much a one-click tailored solution. But on the engineering and development side of things, that's where a lot of the effort is required, right? Building models, collecting data, ground truthing that data, and providing all of that information that we'll talk about in a little bit is much heavier on the engineering side and often very, very niche and task specific, as we'll see later on. To get a bit of a feel for kind of how this looks every day before we look at it geospatially, right? We can think of things like spam removal in our email. I alluded earlier, your streaming platform recommending shows, Google Maps or Apple Maps analyzing traffic patterns and giving you suggestions on routes to take. All of that is machine learning powered. On the deep learning side of things, right, facial recognition software, we even see that in our phone and mobile device photo libraries. Autonomous driving and the recognition and response to objects, making decisions based on our environment and how to respond to them. Perhaps unfortunate to have to deal with, but fraud detection, when our banks alert us, they see spending patterns that are out of the norm of patterns you've had in the past, and maybe we need to address that. Perhaps maybe where we're more interested in, professionally and however we want to think about it, is applying AI to geospatial-based problems. And so I'll be talking through my perspective with Global Mapper, but I encourage you to think kind of outside of that box and other ways you might apply machine learning and deep learning methods in your workflows or look to have them implemented in your workflows. GlobalMapper Pro itself has two AI-powered kind of sections of the app or two tools within the app. We have some machine learning-powered automatic point cloud analysis. So think of, classification and feature extraction from point clouds. And then what we're going to talk about as well, the deep learning side of things, what we call the insight learning engine, and that's really our deep learning-powered image analysis toolset that came out fall of 2024, so it's still relatively new and in beta. We'll start off with the point cloud side of things. So I'm sure many of you have interacted with LiDAR data one way or another. If you've ever heard me or one of my colleagues speak before, we talk about point cloud analysis a lot, given the popularity of the data. Right, point clouds have really grown in size and frequency and the amount of information they can contain, and there's so much that we can learn from this data type. And having the ability to leverage machine learning techniques allows us for more accurate identification and classification of objects in a point cloud. These types of methods also give us flexibility so that users can classify data from a variety of different sources. It wasn't that long ago, even when I was starting in industry, where the vast majority of LiDAR was aerial fixed wing from an aircraft. And over the past handful of years, it has exploded to terrestrial, maybe non-fixed wing aircraft, think UAV, helicopter, photogrammetric. So we have all these different types of point cloud data being gathered, and machine learning methods give us the ability to classify them well. We've also implemented them in such a way that users have the ability to conduct custom training and classification. so that if they're looking for something unique in their point clouds, they can train the tools to go ahead and do so. That process traditionally is a two-step process. So the first portion of this is what's called geometric segmentation. We can think of that quite literally as finding a feature or an object in the point cloud. And we don't know what it is, but based on a set of predefined parameters that in our case can be user adjusted, allow you to find things that are called segments. And those segments are just an object in the point cloud. So if you look at the image on the left, this point cloud has been what we call segmented. And you'll see different building roofs, maybe different trees, different structures and things like that. From here, then the subsequent step is called semantic segmentation. We do this through a adapted maximum likelihood classifier. But what this does is this is the step that gives meaning to the object. So for example, we have some built-in classes, and I'm sure those of you who work with LiDAR are familiar with that, right? Identifying ground, buildings, trees, etc. We have a feel for what these structures look like, and we can search through the point cloud and through the identified segments and find segments that match those criteria and so on. And that's then how we apply a little bit more of advanced knowledge to what we think the objects in the point cloud represent. So we have a variety of built-in classes, like I just mentioned. What we then have the ability to do is train their own model to identify custom classes. So you've identified all your built-in classes, you found your ground, your building, your trees, etc. And now I want to go ahead and find swimming pools. This is where we start to get into some of the more advanced statistics on the tools and working to identify what makes up the structure of a feature. So let's look at that a little bit more closely. I like to use this airplane example just because they're a really unique shape. And so the goal here was to train a new classification to identify airplanes automatically. So after a built-in classification is run, right, and you'll see, so a very left-hand image, I found my ground, my buildings, trees, some power lines, etc. Now, once that's done, I can tailor the parameters used to help identify objects of interest. So if you look at the second image here in the middle, we're viewing that point cloud now by segment. So I've seen all these segments that make up an airplane. And what I can do is provide a few examples, train a classifier, and then run that custom trained classifier on the entire point cloud and identify the airplanes, the pinkish color, all the way over on the right. And this doesn't just have to be airplanes. This can be any feature with a unique geometric structure. I've done it for vehicles, for certain shaped buildings, objects that have really unique colors. I showed the swimming pools there in a screenshot, but think paint stripes on an airport runway, big visible pieces of white on an otherwise black surface. Roads and sidewalks and things of that nature can all be identified as well. So really, as long as we have a clear representation of that feature and it's a consistent representation, I wouldn't expect a airplane train classifier to go find a ship, right? Very different structure. We have the ability to identify those features. Now let's switch gears a little bit and move over to looking at the deep learning side of things. So our deep learning image analysis tools are a component of what we're calling the Insight and Learning Engine. And that is just our new tool set where we're going to put some of these more advanced deep learning powered tools. Right now, it's initially just image analysis. That includes land cover classification, building extraction, and vehicle detection. But we're working on expanding that not only beyond those types of objects, but also to different data types. Think point clouds, terrain, data fusion. So you're looking at multiple types of data at once. And one of the really handy things here is that these models can also be adjusted, or what we call fine-tuned. And we're going to look at an example of that in a little bit. But essentially what that process does is it allows a user to say, my data is a little different than what the model is suited for. If I give it some examples, we can adjust the model and have it better fit our data. So land cover classification in and of itself is not a new task, right? We've been doing it for a long time, even with some older classical machine learning, or yes, machine learning based methods. In the US, we provide a national land cover data set. Annually, semi-annually, that's updated. The goal of this tool is to function on much higher res imagery. So we have this tool trained on meter, sub-meter imagery. So any multi-band raster image, and it allows you to also custom tailor that so you can, adjust if you're working with a little bit finer data, maybe a little bit lower res data as well. So you have the ability to fine tune them too. For example, if we take a look at the classification map image on the right, we're even picking up what looks to be maybe some sort of track being built or something in progress there. So we're really getting, finer scale objects, and we'll look at some live data so we can zoom in a little bit there. When it comes to extracting building footprints, so this process is a little different than land cover, right? Because instead of making a continuous map, although that does kind of happen under the hood, what we're doing is identifying the explicit bounds of features. And so the way this runs is effectively there's a binary raster grid that's created under the hood. It identifies where our buildings are, and then creates a estimated vector footprint off of those features. So your end result here is a vector product representing the footprint of your building features. And these models are trained at, we're talking sub-meter resolution here, right? As we're starting to look at finer scale objects, our resolution has to be higher to capture those objects. So that same kind of train of thought also works for vehicle detection. And in this case, vehicles are detected using a bounding box. The more discrete and smaller the object, traditionally we take a detection route that marks the bounds of the feature as a bounding box rather than the explicit pixel boundary like we saw with the buildings. This works in, suburban settings as well as more urban ones too. So again, image on the right is the inference where we have identified the vehicles in the imagery. And I think what we'll do here before we've got a few minutes left before we run out of time, we're going to go ahead and I'm going to bring open the app just so we can look at a data set a little bit live here. So what we're looking at, I have some imagery loaded into Global Mapper, and this imagery I don't recall is, so resolution's about 1/4 of a foot, or 3-4 inches or so. So relatively high res imagery. And I ran these models earlier just so we didn't have to sit here and wait. But we'll take a look at each tool. And when we launch the tools, they're almost underwhelming. And I mentioned earlier on that on the deep learning side of things, from the user end, it's often, very straightforward. It's you're choosing a model to run and you run it. All the hard work, so to speak, is done on the engineering and development side, where we build the model, train the model, and iterate through that over and over again. The user then gets a very straightforward, I need to classify land cover in this type of imagery, go ahead and start to inference. There's very little that a user needs to do here. That holds true for both building extraction and vehicle detection as well. And really, the app will automatically identify the type of raster imagery you're working with, choose the best model, and run it. So fairly straightforward from the user perspective. Let's take a look at, to start, we'll take a look at land cover. So this imagery that we're working with is actually quite a bit higher resolution than what our model was trained on. So we trained on about 1 meter, and this data is quite a smaller fraction of that. So the model wasn't great. For example, we'll zoom in here, my inference, right? My water doesn't look great, and I say doesn't look great based on a visual comparison to the water bodies here and here. I also noticed, we had some water in and around these houses. That's probably incorrect. And this water body doesn't look great either. So I had mentioned that we have the ability to let people adjust their models. And so what they can do is launch a tool called the fine tuning tool. And I'm going to go ahead and adjust my land cover. And now we can do one of two things. Users can load reference data or go ahead and generate their own training data. And what I did, I can use these tools to draw and manually correct some of the bodies of water to more clarify, say, okay, this is definitely water. These pieces, parcels down here are not water, et cetera, et cetera. Starting the training takes in all that information I provide and adjusts the model. So what we'll do is we'll then compare now the resulting model, at least around the bodies of water, because that's what I focused on for this example. And we'll see now how much cleaner that data set is in and around the water. So it really gives us a very powerful tool in addition to the initial inference, but also allowing us to adapt and adjust for data that may vary a little bit from what we've trained on. The vehicle bounding boxes, again here, let's see how this did. So I ran a vehicle inference on this data set too. Overall looks pretty good. This data is more or less in line with the resolution of the model we trained. Maybe a little funky there. Maybe we got an extra vehicle or something, but overall did a really nice job of identifying all of our vehicles. Overall, same could be said for building extraction as well, so I can identify building footprints. I had mentioned earlier the binary map. So we can generate this as an option, just gives the user a way to see the raster version before we vectorize our buildings and extract them. I know I'm getting short on time here, and there's plenty more I could always talk about. Well, let me try to stay on track and kick back over here to what I wanted to talk about. So if you're interested in using any of those deep learning tools, they're available in the pro version of the app now as part of that license. There'll be more updates to come later in the year in that regard. I would be remiss if I didn't also mention GlobalMapper really is a complete solution to the vast majority of geospatial workflows, again, whether we're talking point cloud, terrain, imagery analysis. I think the important takeaway, though, from the AI-powered side of things is to get us past all the buzzwords and all the jargon and really begin to think about how we can apply these tools to everyday tasks and problems that we want to solve geospatially. I think that's where we will really see a benefit, both as users of these tools, but also as people making those informed decisions, whether it's in industry and work, play, whatever the case may be. So I think there's a lot of potential there to come in the future.